The last portion of this lesson talks about the intermediate value theorem. Suppose f is continuous, so f must be continuous on a closed interval from a to b, and let n be any number between f of a and f of b. Let's say a is right there and b is right there, and let's say f of a and f of b, and let n be between the two values. So let's say n is somewhere in there. If the function is continuous, no matter how you do this, you can't lift your pencil off the board, then there must exist a c in the open interval such that if you take f of c, that would be the n. What we do, instead of showing this, which is a lot of work, what we do, we make an alternative proof, and that is, we take f of c and we shift it down that many units. That will be our n. That means f of a will shift down that many units, and f of b will shift down that many units. So we subtract n from each of those. And now, all what we have to do to show that there's a zero, we show that one end is negative and the other end is positive. And if f is continuous, one end is negative and the other end is positive, or vice versa, zero must exist in there. That makes it a lot easier to show. So, example 9, use the intermediate value theorem to show that there is a root of the given equation in the specified interval, meaning suppose that between those two, between 0 and 1, there is a c in there where those are equal. What we do, we say, well, let f of x equal, and we move everything to one side. Meaning, by moving this, we're trying to show there's a 0 there. So, square root of x minus 1 plus x equal to 0. And all what we have to do is show that f of 0 is negative 1, f of 1 plus 1 is 2 minus 1 is 1. So that works. Then from this we say f, which is radical x plus x minus 1, is continuous on the closed interval from 0 to 1. It's continuous everywhere where the domain exists. F of 0 is less than 0. F of 1 is bigger than 0. Therefore, there exists a c in the open interval between 0 and 1 such that f of c equals 0, meaning the square root of c minus 1 plus c equals 0, And if you move that over, that will mean the square root of c minus 1 equal negative c, which is what we're trying to prove by the intermediate value theorem. You must state that it's continuous, otherwise this doesn't work. Here's another example. Same deal. We say let's say g of x equal x squared minus x minus the cosine of x. So we move everything to one side, 0 on the other side, and we check. The g of 0 is 0 minus the cosine of 0 is a negative 1. The g of 2 is 4 minus 2 minus the cosine of 2. The g of 2 is, so this is negative, 2 minus the cosine of 2. Recall that for any value of a cosine, the smallest this could ever be is a negative 1 plus 2. That is positive for sure, without knowing exactly what cosine of 2 is. And now we state the same thing. G is continuous. You must, because it's a polynomial and a sine or cosine, they're always continuous on the closed interval from 0 to 2. F of 0 is negative. F of 2 is positive. So out of those, we know that there exists a c in the open interval between 0 and 2 such that f of c equals 0 by the intermediate value theorem. Hence, c squared minus c minus the cosine of c equals 0. And if you move it to match, that would mean c squared minus c equals the cosine of c. I tried to fit that after the last lecture, but for some reason it wouldn't do that. So there it is. That concludes this section.